Hello, everyone. My name is Spyros, and today we will talk about how we made our app scalable by how we organize it and how we used and utilized the Kubernetes that George presented earlier in order to scale it. So, as I said, my name is Spyros. I'm a software and DevOps engineer, and I work for the last 3.5 years at Yodek, and I'm curious about tech. I always like learning new things and experimenting with new technologies, and I like solving problems, especially the ones that we will see today. So, I will start from where George left it previously about stateful and stateless applications. And we will describe first what's the difference between a stateful and a stateless application. So a stateful application is an application that stores and maintains data for interactions or between user interactions, and it uses memory or the file system to do it. And some examples are some old traditional web applications that store cookies on the machines that serve the application to serve the data, or even some databases. It doesn't need to be a web application. And on the other side, a stateless application, it doesn't store any session-specific data for user interactions. Each request is treated differently, and it's self-contained, and it allows your application to be highly scalable. So as we can understand, we need a stateless application to manage to scale our app. So we at Yodek have a CMS application that our customers use to customize content that is shown in their monitors, in their screens. And for that, the application server that did all the job was something like this. It was an R5 2 extra large AWS EC2 instance that had 8 virtual CPUs and 64 gigabytes of RAM, and consisted of a Django application, that is our main web server, a Celery application that is a task running software, Celery bit that manages some scheduled tasks that the Celery actually executes. And on the same machine, we had a Redis that was used as a cache, and the RabbitMQ that did all the task and queuing between the Django application and Celery bit. So we had the big question around 4 years ago that it was also asked to me: how do we scale? How we take this virtual machine that we had and increase the number of them so we can serve more customers? At first, we had to begin with monitoring. If you can't measure it, you can improve it. And to be honest, we didn't have any clue about what was happening inside our machines, how much CPU we were using, how much RAM our instances were using. So we had to stand on the shoulders of giants. And one of the first things I did when I started in this position is to install Prometheus and Node Exporter in all of our instances. In case you don't know, Prometheus is a metrics scraping and storage application that you run exporters in for each service you want to monitor, and Prometheus is responsible for querying the data from these exporters, storing them, and then we used Grafana to visualize all this data. At first, it was just a simple EC2 instance, but later on we used Mimir that allowed us to store all the Prometheus metrics in S3. So one of the first things that we did after we started monitoring our instances was to move everything that wasn't like our application code outside of the VM. We had, as I said earlier, RabbitMQ and Redis. And at first, they were installed alongside our application because in the first steps of the company, things were more cost sensitive. So we didn't want to spend more money on paying to Amazon just for hosting a Redis or a RabbitMQ cluster. But the problem with hosting them on your instance is that they might require to scale along with your application. As more requests hit Django and more tasks were queued in Celery, this meant that RabbitMQ had more traffic to handle, and it was competing for resources with the rest, the core of our application. So when you migrate to managed services, you might pay a little bit extra. For AWS, it's like a 10 or 15% extra of a similar EC2 instance, but you will get rid of all the maintenance, of all the backups, all the security patching, and all the updates. So at the end, when you start scaling, it's a same thing to do. After that, we decided to investigate why we were using 64 gigabytes of RAM for our EC2 instance. This way, we wanted to optimize every aspect of the three main components of our application and later scale them independently. So we had some issues with Celery that had some memory leaks, and we will see every time that after a restart, the RAM usage continually was increasingly as time passed. Using some external libraries, like we noticed that with Redis Spy, that also had some memory leaks and left some open connections. These make things worse. So Celery, to solve that, has a flag because they recognize that they have some issues. They have a flag that kills the spawned instances after they execute an X amount of tasks. And as you can see, after restarting and applying the flag that we saw earlier, the RAM usage stabilized, increased a little bit, and then when the restarting kicked off, the memory went back down. So we searched for the best trade-off between RAM usage and the CPU overhead of constantly recreating Celery workers, because we could set this amount to 1 or 2 tasks, but then probably your application will spend more time recreating workers instead of actually running the task. So we settled for a number around 400, and it serves us well so far. After that, Celerybit. Celerybit is as I said, a scheduler for Celery. It stores a schedule of tasks that will need to run periodically, and for example, it has a cron tab-like syntax. And we have a task for retrying some unpaid invoices every 2nd, 8th, and 15th of the month. And by default, it stores the data and the schedule of when it runs its task in a file by default. This used to be an easily corruptible self-database. Self-database is a database that is included in the Python standard library. I haven't worked much with it, but my experience with Celerybit database was not great. From what I saw, they seem to fix this issue, but back then when we had the database in a file, when this file was getting corrupted, Celeribit refused to restart. So we had to manually go and check what was going on with the database, and tasks are not scheduled. So for that, we wanted to move this database file outside of an actual file and move it to an actual database. And we experimented with the Django Celeribit package that allows you to store all this metadata inside the database that Django uses. But as we saw in this example, the library is not fully implementing this kind of syntax. I'm showing this because we actually had issues with this function. And we decided first to look if there is any other alternative, and then try to fix the database and check that everything that we have works and it works correctly. And this is where we stumbled upon Redbit. Redbit is a library created by a guy who used to work at, I don't remember the company, but Heroku, yeah, it was Heroku. And actually Heroku uses this in their production system. And what it does, it stores all this metadata in Redis, and also provides you with a log that only one Celeribit instance gets. So in case you run a second or a third instance, the rest of the instance is blocked, and you will not get double or triple the task that you wanted to run once. So after that, we moved Celeribit outside of our instance, and we got only Django and Celery that needed to be improved, because to be honest, Django and Celery use almost similar code with minor differences. So to make these applications scalable, we realized that we should avoid writing data to files. We had some cases that we stored state in files inside our instances, and this shouldn't be the case, and state should only live outside of the application, or the entire instance in a different instance, or in a centralized instance, or in a managed service. In our case, we stored, for example, audit logs in files, that we had a task that ran every night, and parsed these logs and separated them for each account, and then uploaded those files to S3. So what would happen if we scaled our application? We couldn't ensure that the task that performs this rotation would be a specific instance, and also you can't ensure that the request will hit only one instance. And if it does, then you don't have scaling. You just pinned to a single instance. So what we did, we moved all this logic outside of log files and stored them in database, and the task, instead of reading from files, it reads from the database. Secondly, we realized that you should avoid reading data from files, and that your application shouldn't rely on files that were generated by itself, or that files that it generated for any reason, that it will always be there. And as a rule of thumb, just don't create them in the first place. we had a strange case with Zoho SDK. Zoho is what exactly is Zoho? Because Zoho is our CRM instance, and by default it persists the authentication token in a file. So if we scaled our application, multiple authentication tokens would be created, and as we read from their documentation, they would compete on what's the latest authentication token and who has the permission to do what. Thankfully, they provide the base class that you can extend, and we moved also this token to the database. Another thing that you shouldn't do is to store sessions in memory and instead store them in the database. Every web request is stateless. So when you want to use an application or log in any website, the website will send you a piece of information that you will need to provide it to it every time that you interact with the application. And there are two ways of storing this information. One of them is store every data inside the cookie, and the other is store all this data on a server. The server generates a unique UUID or a random string. It's called the session ID, and then passes this to the application, to the client, and the client uses that for authentication. Usually web servers prefer session IDs, and developers do as well, because it's harder to tamper with. You can expire it whenever you want, just in case something goes wrong, or you are not sure of the content, or you just perform an update and all the session needs to be invalidated. You can store more data than cookies, because with cookies you will have the overhead of sending in every request all this piece of information. But the problem is that by default, a lot of web servers stores this session data in memory. So if you scale your application, what happens when your request gets spread across multiple servers? So you will get authorized in one, and then on the next click you do, you will be unauthorized, and all this web navigation experience will be frustrating. So Django has an easy way of storing all these sessions in the database, and also it has an easy way to utilize the cache and the database utilize the cache as a write-through DB. So when it creates a session, it stores it in the database and also stores it in the cache that you specified for faster retrievals. And this is how you can configure this in your Django application. And another big thing that we wanted to tackle is how to do actual zero downtime rolling updates. Because when you have a lot of pods, a lot of containers, you don't want to completely kill every request that comes and spin up all the new containers with the latest code. We are using UWSGI, that is an application server and a protocol that serves Python applications, but also it can work with Perl and I don't know any other language. We are using UWSGI that loads the Django code, and an Nginx server communicates directly with the UWSGI and serves the content to the pages to the clients. So when you have a single server, things are easy, or where used to be easy. You just log into the instance, you pull your code, you perform the Django migrations, and then you gracefully reload the workers. And actually, UWSGI allows you to do that easily by using this configuration value. If you touch this file, it will gracefully reload workers one by one. When we moved our application to Kubernetes, we had to design how it will be configured and architecture. So we settled with 2 containers inside one pod. One is the UWSGI, and the other one is Nginx. They have a common mount point that UWSGI and Nginx communicate with a proxy. And as George said, we had 2 readiness probes that helps Kubernetes know when the application is actually ready to serve requests. So for Nginx, we created a custom /health endpoint. When this returns 200, Nginx is healthy. And for our application, we just did the get to our login page. So if those 2 are true, it means that our pod is up and running and ready to serve requests. So when we have a service in front of our 2 pods, and when a new pod is created, it will be added to the service, and Kubernetes will load balance and round robin requests between those 2 pods. In front of those 2 services, we are using the AWS application load balancer that is native to EKS. So we had at first to see what happens when we scale down our application, because when you scale up, it's easy. Kubernetes handles everything by using and utilizing readiness probes. So when the pod gets terminated, Kubernetes will send a sigterm signal, just like Docker does. But UWSGI by default brutally reloads the UWSGI workers and never kills the actual process. So we had some pods waiting in the terminating state because it had the timeout to pass in order for Kubernetes to brutally kill the pods. UWSGI docs recommend to use this flag, the die on term flag, in order for UWSGI to respect the sigterm signal. But when we tried it, we saw that this brutally kills all workers and doesn't actually work with how you would expect sigterm to work. So allow all the in-flight requests to conclude, and then kill every worker one by one. So you can trap the sigterm signal with this configuration in UWSGI, and when it sees a sigterm, instead of killing every worker, it will call the gracefully kill them all that actually kills one worker after it, when it doesn't serve any requests anymore. So UWSGI actually can expose a FIFO that you can use to interact with it. You can echo things to inside this FIFO, and it will perform different tasks like reloading the logs when you do a log rotation, or reload the code instead of using the reload file that we saw earlier. And you can use this FIFO to gracefully kill all the workers. So by using this lifecycle hook, we actually saying to Kubernetes that before actually trying to kill the workers, execute this command, and this will send the signal to UWSGI to gracefully kill the workers. But we still didn't reach the zero downtime that we wanted. We were still receiving some 502 responses. So after some investigation, we realized that because we are using the load balancer provided by AWS, when a pod it gets created, it is added to the target group of this load balancer. And AWS has its own, the load balancer from AWS has its own health checks included, and it will actually serve traffic to the pod when this health check passes. So when the pod is ready from ALB side and not from Kubernetes side, traffic gets sent to it. But when we were downscaling and pods were getting killed from Kubernetes, ALB doesn't handle this very quickly, and it had to take it took some time for ALB to actually realize what was going on and start for the health checks to start failing and deregistering the pod from the pool of ready to serve targets. So as we can see, forcefully, ALB thought that this pod is healthy, but Kubernetes was trying to kill it. This didn't take long. It will take as much as you configure your health checks to be, but the lowest values you can set is you will need to have 5-second checks that will need to fail 2 times. So for that, we can use a readiness gate. What readiness gate does, it injects some extra data to the pod. And now this pod contains the information from the ALB point of view. And when a new pod gets created, it will have to pass the readiness checks from Kubernetes and the readiness checks of the ALB in order to be considered healthy from the Kubernetes. And in case of a rolling update, it will need for those two checks will need to be true in order for the rolling update to continue. So in case of downscaling, it will need first the readiness probe of Kubernetes starts failing, it will inform the ALB, and the ALB will start draining the node and move the pod outside of the ready-to-use targets. And it's very easy to use these readiness gates. If you are using the ALB operator, you just need to tag your namespace with this label, and you will need to recreate all your pods because it will not be added automatically to existing pods. So, where are we today? After doing all these things that we saw earlier by moving all the state outside of our application instances, and by moving all the external dependencies outside of our instances as well, we can have an X amount of Django workers, an X amount of Celery workers, as well as Celery bit workers, because they are using the the log provided by Redbit. So actually only one Celerbit worker will run. We are using a RabbitMQ cluster that we are currently hosting, and we are considering also migrating it to a managed AWS service, but we didn't do it from the beginning because actually to create a RabbitMQ cluster, it's pretty expensive in AWS. And we took our database that was also in an EC2 instance and Redis and just migrated them to RDS and Elasticas. So I thought I went a little bit faster than expected. But to be honest, I'm pretty thirsty. I forgot to bring water. So any questions? Yeah.
So you talked about reloading code.
Yeah.
I'm a little bit confused. I was expecting that, when we have new code to ship, we build new container images and we ship those to the pods, right? That's what we do in Kubernetes world. So how is that? I don't know. I'm a little bit confused there with how the code makes it into the running container.
That was when we were in the state that we saw at the beginning. I didn't make this clear probably, but when we had a single server that contained everything, we had the UWSGI running as a system service, and the code just not mounted, but pulled inside a path in the file system. So we didn't have any containers, we didn't have anything like that. So someone had to actually go to the server, do the git pull, and then do all the migrations and the chain reloading that we saw here. So yeah, right now we are utilizing Argo CD, and what we do is we ship the code inside the container, and Argo CD allows you to have a pre-sync hook that when a new container image gets built and it updates our manifest with the latest tag, Argo CD picks up these chains, and before it starts creating stops the old pods and create the new ones, it will run the pre-sync hooks. So in the pre-sync hooks, we run the migrations, and when the database migration completes, then it will start the rolling update procedure.
So there is still a risk there with a long-running database migration that could cause some downtime during the
Yeah. We haven't faced this so far, but we will solve it probably when we'll see. Yeah.
So first you run the migration, and then you deploy the pods, right?
Yeah.
Από ό,τι βλέπω, γυρίσατε πάρα πολλά από τα services σε managed services. Έχετε υπολογίσει τη διαφορά κόστους του Crete και μετά. Αυτή είναι το первο αντίδραση. Αυτό το πρώτο. Δεύτερον, αν έχετε υπολογίσει το κόστος, αν χρειαστεί, όταν χρειαστεί, να κάνετε migrate από την AWS σε έναν άλλο πάροχο, πόσο θα στοιχεί στην εταιρεία.
Ναι, τα έχουμε υπολογίσει και τα δύο, είναι η αλήθεια. Το κόστος συγκεκριμένα για τη βάση έβγαινε όντως ένα 10 με 15% πιο ακριβό, γιατί έτσι δουλεύει το RDS, το οποίο κάπως το περιορίσαμε γινώντας το instance Graviton. Επειδή η βάση δεν είναι δικός μας κώδικας, δεν πρέπει να είναι optimized σε Graviton, αλλά η Postgres έχει γίνει ήδη, τουλάχιστον το έχουν φροντίσει άλλοι, το να μπορεί να τρέχει σε ARM επεξεργαστές, χρησιμοποιώντας Graviton. Ουσιαστικά ισοφαρίσαμε το κόστος και κρατήσαμε τα ωφέλη του κάποιος να πατσάρει τη βάση για να ξέρουμε ότι τα backups δουλεύουν. Τα έχουμε δοκιμάσει κιόλας γιατί χρειάζεται να κάνουμε κάποια restore συγκεκριμένων πραγμάτων. Όσο για το κόστος, η βάση μας δεν είναι τόσο μεγάλη ώστε να έχουμε πρόβλημα να τρέξουμε ένα SQL dump, το οποίο θα το πάρουμε και θα το στείλουμε κάπου αλλού. Αυτό, δηλαδή κινούμαστε στα 100 GB συμπλή. Το πραγματικό μας κόστος είναι τα media που χρησιμοποιούν οι χρήστες για να δείξουν στις οθόνες τους. Αυτό, η βάση απλά περιέχει pointers στο πού είναι το κάθε media, ότι δεν έχει πολύ.
Δηλαδή, θες σε περίπτωση που χρειαστεί χωρίς να κάνεις προφίλ στο provider, να πας στην Google, ο τρόπος να κάνεις στην Google. Ή θα υπάρξει κάτι.
Θα υπάρχει πρόβλημα εάν, βασικά εξαρτάται από το λόγο που θα πούμε ότι θα φύγουμε από την Amazon. Εάν η Amazon απλά μας μπανάρει, θα έχουμε τεράστιο πρόβλημα, γιατί δεν θα έχουμε την ευκαιρία να πάρουμε όλα τα...
Όχι, δεν εννοούσα. Αυτό είναι σαν χρειαζόταν να κάνεις
όχι, από πλευράς database data είναι φθηνό. Από πλευράς S3 bucket είναι πάρα πολύ ακριβό.